Hello and welcome to the last installment of the Chapter 6 Problem Bank. Today we will be talking about explosions, and we start with number 31. A 75 kilogram swimmer dives horizontally off a 500 kilogram raft. If the diver's speed immediately after leaving the raft is 4 meters per second, what is the corresponding raft speed? Now we call this an explosion because we have a swimmer and a raft that are originally or initially connected or one mass, and then after the occurrence takes place, they are two separate masses. So we start off with what is given. The mass of the swimmer is equal to 75 kilograms. The mass of the raft is equal to 500 kilograms. The final velocity of the swimmer is equal to 4 meters per second. And for right now, looks like we will assume that the initial velocity of the combined two is equal to 0 meters per second. So our unknown is the final velocity of the raft. Our equation, just a conservation of momentum equation with a little twist because we have one mass, one combined mass, which means that there's only one velocity. So we have V sub initial times the mass of the swimmer plus the mass of the raft is equal to the final velocity of the swimmer times the mass of the swimmer plus the final velocity of the raft times the mass of the raft. Substituting everything in, our initial momentum because of our velocity will be 0. 0 times any mass will be 0. The final velocity of the swimmer is 4 meters per second multiplied by that mass, which is 75 kilograms, plus V sub FR, which we will be solving for, multiplied by 500 kilograms. Solving that, we see that 4 times 75 is 300. Bring that over, so a negative 300 kilograms meters per second is equal to V sub the final velocity of the raft times 500 kilograms. Divide both sides by 500. See that our kilograms cancel out, and that our final value V sub FR is equal to a negative 0.6 meters per second. Yes, negative 0.6. What that means is that because we originally called our swimmer's velocity positive right here, that is telling us that our raft is going in the opposite direction of our swimmer. And that is our final answer. Number 33 states, and the astronaut weighs 60 kilograms. She is spacewalking outside the space shuttle and pushes a 350 kilogram satellite away at 0.9 meters per second. What speed does this give Anne as she moves towards the shuttle? So again, we will assume that our initial velocity of Ann, the astronaut, and the space shuttle, or excuse me, and the satellite at 0. The mass of Ann is equal to 60 kilograms. The mass of the satellite is equal to 350 kilograms. The final velocity of the satellite is equal to 0.9 meters per second. Our unknown is the final velocity of Ann. Our equation, the same as number 31, will be our initial velocity of the two plus both masses, mass of the satellite, mass of Ann. So that gives us our total momentum initially is equal to the total momentum final. So we have the mass of Ann times the velocity of Ann plus the mass of the satellite times the velocity of the satellite. Substitute everything in. This will be 0 because our initial velocity is 0. So this is equal to 60 times v sub fa plus 350 times 0.9. Running some calculations, we see that 0.9 times 350 is 315. So we subtract 315 from both sides. We end up with negative 315 is equal to 60 times v sub fa. Divide that by 60. And 315 divided by 60, or negative 315 divided by 60 rather, is equal to negative 5.25 meters per second. Again, that negative is just showing that because Ann pushed away the satellite, and we call our satellite's motion positive, that Ann will be going in. Number 35, a miniature spring-loaded radio-controlled gun is mounted on an air puck. The gun's bullet has a mass of 0.005 kilograms, and the gun and puck have a combined mass of 0.120 kilograms. With the system initially at rest, the radio control trigger releases the bullet, causing the puck and the empty gun to move with a speed of 0.5 meters per second. What's the bullet speed? So writing down our given. Again, we are showing that we are initially at rest, so the velocity initially is equal to 0. The mass of our gun and puck is going to be 0.120 kilograms. The mass of the bullet is equal to 0.005 kilograms. The final velocity of the gun is equal to 0.5 meters per second. Our unknown will be the final velocity of the bullet. Our equation will be our initial momentum is equal to the final momentum of the bullet, which would be the final velocity of the bullet, multiplied by the mass of the bullet, plus the final velocity of the gun and puck times the mass of the gun and puck. Substituting everything in, 0 is equal to final velocity of the bullet times 0.005 plus 0.5 times 0.120. Solving, 0.5 times 0.120 should be 0.06. Negative 0.06 is equal to final velocity of the bullet multiplied by 0.005 divided by 0.005, cancel that out. The final velocity of the bullet is equal to negative 0.06 divided by 0.005. And our final velocity of the bullet will be negative 12 meters per second. Hence the toy gun not shooting a bullet very fast by bullet standards. That concludes chapter 6.